So we are in Introduction to Statistical Learning, Chapter 6. We are in the conceptual questions here still, and we're on question 6. Okay, so here we're going to explore two different equations. One is the loss function, 612 is the loss function for ridge regression, and then 613 is the loss function for lasso regression. Okay. So in both of these, we're going to be doing something similar. So I'll read the ridge regression question here. So consider the equation 612, again, the loss function for ridge regression with one parameter. Okay, so in other words, these summations are really only taking place over one parameter, one beta. For some choice of y1, or I think that might be yj, but where lambda is greater than 0. Now, we're meant to, with a plot, confirm that the estimate for beta is this right here, under that circumstance, right? So with one parameter, the ridge regression beta parameter should be this for a given lambda. And so we're supposed to plot that. And then similarly, for the lasso part, we're supposed to show through plotting that for some lambda greater than 0, that the beta coefficient should equal this right here. I think that should be beta 1 since we're just looking at one of them, but anyway. So let's start with the ridge regression. So here I've just reproduced that whole question right here. What I want to do is to first solve this analytically, and then we will do it graphically. Okay, so we have our loss function here. Okay, and so we can expand that right with just one beta coefficient, one parameter. We're summing over one thing, so we get this and we get this. Okay, and that expands to this. Well, to this. Okay, and so now if we want to find the appropriate beta coefficient, then we need to take the derivative of this guy and set it to 0 and then solve for beta. And so when you do all of that, you in fact come out with the estimate for beta being that right there. Okay, and that is exactly what we were meant to show. Okay. Now to plot that, or to use a graph that actually maybe demonstrates that. So here's the plot, but let's just look at what's happening here. Okay, so I'm arbitrarily picking a y value and a lambda. I'm just setting them both equal to 1, but you can play with those. And then I'm going to test a bunch of beta values from -10 to 10 by 0.1. Okay, so a bunch of different beta values. And now I'm encoding my loss function. Okay, that's the thing I'm going to end up plotting actually. Okay, so that is that thing right there is, well, it's this. Okay, and now I'm going to plot the loss against all of the different betas, so I'll get the loss for each beta. So that's all of this. And now I'm going to put a red line at y over 1 over lambda, which is what we solved for right there. Okay, so that red line represents our analytical solution. And then I'm putting a point at the minimum of the loss function, okay, which is right there. All right. Okay, I just recognized a small error in the code. So if you rewind, you'll see that I changed this bit right here. I'm not sure why I had the other way, but we find the minimum of the loss function. We plot it against the beta that corresponds to the minimum of that loss function, and we see that it completely intersects with the analytical solution right there. Okay. So now we're going to do the same thing for ridge regression. Okay, for ridge regression. So this. Okay. Now this one looks a little bit more challenging because we see that beta is kind of broken up into these different segments here, depending on the relationship between y and lambda. Okay, but we're still going to try to first solve this analytically, even though the question doesn't ask us to. Okay. So we have our loss function here. Okay, and with one beta, or I'm sorry, with one parameter beta, then all of that simplifies to this guy right here. Okay, And now we can take the derivative of this and we get this right here, okay? And this little guy is always a little bit funky, all right? Now, but what is this guy? You can think about this as actually being the sine of, right? So think about whatever beta is, okay? So let's take beta is 13. Well, 13 over the absolute value of 13 is 1, okay? So we're multiplying lambda by 1. But now think about if lambda is negative 13. Well, now we have negative 13 over the absolute value of negative 13, so we have a negative 1. And so now I'm multiplying lambda by negative 1. Okay? So now the next thing I need to do in order to solve for the beta that minimizes my loss is I need to set the derivative equal to 0. But because of this absolute value thing here, I'm going to have 3 different possibilities, okay? I'm going to have for situations where beta is greater than 0, right? And then this becomes just multiplying by positive 1. Where it's less than 0, okay, now I'm multiplying lambda by negative 1, or where beta equals 0. All right, so I have these 3 possibilities. All right. So when you set this equal to 0, you can do the math for yourself. But we get, and you're solving for beta each time, okay? And again, you can drop this and you can just multiply lambda by the corresponding positive or negative or whatever. You get these values, okay? Now these values correspond here, okay, to what the problem said that we would get, but so far we found it when beta is greater than 0, when it's less than 0, da 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 da. And so that doesn't really help us because we don't know beta, we only know y. But notice that this expression is beta, and so it's really y minus lambda over 2 greater than 0. So I can find a value for y which makes beta greater than 0, right? So I would just take the lambda over 2 over to the other side, right? So if y is greater than lambda over 2, then this is the expression for beta. And similarly for over here, okay? If y plus, if y is less than lambda, negative lambda over 2, right? Well, now I get, right, so I'm going to take the lambda, I'm going to take it to the other side, right? So if this wasn't here, I'm subtracting lambda over 2 from both sides. So now I get y is less than negative lambda over 2, and in that case, I know that beta has to be this, okay? And then now this derivative is actually undefined when beta equals 0, but if we just kind of use the rule that this is this is the sign of that and it's 0, well then what we get is we get negative. This thing simplifies to negative 2y, and then we set negative 2y equal to 0, in which case y equals 0. So anyway, so we can translate this into this, and this is exactly what we're given in the problem. Okay, so we've solved it analytically, and so now we're gonna graph this. Okay, and so I'm picking a lambda. I'm arbitrarily picking a lambda, and then I'm picking a y value that is necessarily greater than lambda over 2. Right, so I divide lambda over 2 and add 1. Now I'm picking a lambda that is necessarily less than negative lambda over 2, and now I'm picking a value where lambda is the absolute value, or I'm sorry, where lambda where y is equal to the absolute value of lambda over 2. Okay, so all right. So now for each of these, I need to calculate a different loss function. And that's what I'm doing here, right? For each different y value. And then I have my analytical solutions, which we just found, and I'm encoding those as B1, B2, B3, beta 1, beta 2, beta 3. Okay, and now I'm going to plot that, right? So I'm going to plot, the first y, right, where y is greater than lambda over 2, where it's less than lambda over 2, and then where they're equal. All right, and so here's the 3 plots, and let me just open this up in a new image here. Okay, So here we have lambda, or y is greater than lambda over 2. All right. So so I've drawn, what did I do? I drew, yeah. So I drew lines at our analytical solutions, and then I put points at the minimum of the loss function, right? So the points are taking place where we found the minimum of my calculated loss function at the beta that corresponds to that loss function, okay? And you see that they line up here. So we've shown it analytically as well as graphically. Okay, we'll call that good.